Okay, so on this video we're going to talk about another type of electrophilic aromatic substitution. This particular case we have an acyl substitution, and we have here our acyl group, and we have a benzene ring. As we learned before, our benzene ring works as a nucleophile. We have here our electrophile, and then we use an aluminum chloride and a little bit of heat, and then we make our acyl connected with our benzene ring. And for this particular case, we have our aluminum chloride working as our catalyst. So basically, one of the lone pairs in the Cl will do the attack, make this Lewis acid, making this complex here that will ended up in a Lewis acid and base structure, or Lewis and acid complex. So we dump one of the lone pairs, make this triple bond, kicking out the Cl. So we ended with that plus AlCl4. So we form this intermediate here, which is the most stable one. And if we want to show the resonance structure, we can just pull back the lone pair in the oxygen, having a double bond, and we have a carbon holding the plus charge. But remember, the most stable resonance structure will be the one that has the charge associated with the more electronegative atom. Therefore, this is the most stable unresonance structure. So when we talk about alkylation, we said that we need to look for rearrangements. It's one of the particular consequences about that chemistry. In this one here, and I had a note here that we say we should not look for rearrangements. No rearrangements can occur. And the reason for that is because in this particular conformation here, I have every single carbon and oxygen following the octet rule. If I do a rearrangement here, I ended up with one carbon that has 6 electrons, which is not stable at all. So even though we have a plus charge here, this guy follows the octet rule, and therefore it's more stable. So we cannot say that we have rearrangements under acylation conditions. So we do not claim for rearrangement, so you guys don't need to worry about rearrangements. But once we have this particular structure here being formed, now we can do our chemistry. That is basically the same thing that we have been doing since we started talking about this chapter. So if you remember, we have here our nucleophile. Okay, and what we do, we need an electrophile. In this particular case, I'm going to use the most stable resonance structure with the charge associated with the oxygen. And now we break the aromaticity. Okay, it's a slow step because it's the formation of a carbocation. This is a allylic carbocation, so it's more stable than the normal carbocations we were dealing with. Okay, we added our electrophile. Now we need some sort of base to come and pull the hydrogen from that particular position and restore the aromaticity. Remember, we do not claim that we have the nucleophilic attack, because the nucleophilic attack will end up in a product that is not stable at all because it's not aromatic. So we use that to come and make it working as a base, grab the hydrogen and restore the aromaticity. Grab a hydrogen, restore the aromaticity in a fast way. Okay, plus, I would just draw this again. Let me just redraw this. This is a Cl, and now Al minus 6. So we grab the hydrogen there, we ended up with that product plus our catalyst. So just a review for this particular reaction, remember we have our acyl group, we make the complex, and then we ended up having this electrophilic being formed. We have two structures that are resonance structure for this particular case. Remember, the resonance structure shows that the molecule is not this one, it's not that one, but it's something between, it's the average between these two. We know that most of the time the conformation will be that one, because this is the most stable conformation once the plus charge is associated with the more electronegative atom. And we said that we cannot claim deformation or rearrangements in this particular case, and the reason for that is because this rearrangement ended up in a molecule that is not following the octet rule, so it's not stable at all. So we keep on our molecule as it is and without any rearrangement. So then we have our nucleophile. Our nucleophile comes in our electrophile, do the attack, added the electrophile into the benzene ring. However, when it do that, it break the aromaticity, ended up in this carbocation here, which is a allylic carbocation, a hexadienyl carbocation, which is more stable than a normal carbocation that we're dealing with. However, we don't want it stay in this conformation because this is really unstable compared to my initial reactant and my product. So what happens is that some sort of molecule comes and works as a base, grabbing the hydrogen, pulling back my double bond, and restoring the aromaticity, which is and ended up in a product that is more stable, has less energy, and we have the addition of our acyl group there, plus HCl, plus our catalyst. So this is the overall reaction, and this is the mechanism reaction for this particular chemistry.